offshore wind and transmission. So offshore wind and transmission technology it's an immature area and it's new in its infancy. So there's a lot of ability to influence the designs, the standards, the technology, the way you want to drive it. So it's a perfect opportunity. And today I'll walk you through some of the nuances when it comes to grid forming technology and how it's been playing a role in offshore wind industry and what the future really looks like with such a technology. So if we move to the next slide, Ben. Next slide, please.
When you have control on your side.
Okay. Can you hear me? Can you see the slides changing?
Oh, now I
can. We see slide number 3 right now.
Yeah, we are on slide 3. I can see it now. So I think a couple of things I want to do before we get into the grid forming technologies, just go a little bit into about the company Ørsted. And I'll do a very quick intro of the company. And after that, we'll get into a little bit of offshore wind and how it's played out in the US market and get into the details of grid forming technology. If you move to the next slide, please. So Ørsted, in the US, we have a whole spectrum of clean energy solutions. It's offshore wind, onshore solar, and storage. If we move to the next slide, please. This gives you a map of the US portfolio, all the offshore and onshore wind and solar and battery energy storage projects we have under development or in operation. And we're also into hydrogen, or what we call as P2X business. That's something that's not shown on this map, but that's another part of Ørsted's US business portfolio. If you go to the next slide, please. From an offshore wind perspective, we have had over 30 years of experience as an organization. A lot of it in US, a lot of it in Europe primarily. The first US wind farm is the Block Island wind farm. It's very small in scale, and none of the wind farms that you would be seeing in future is going to be this small. So this is just one of a kind offshore wind farm that was developed more like an R&D project, I would say. The future that we would be seeing is of the orders of gigawatt scale wind farms. And we have about 7.6 gigawatt of installed capacity offshore and about 5 gigawatts of offshore wind in the US portfolio. And this 5 gigawatts, a lot of them are in various stages of design, construction, and development. It's real. And the scale that we are seeing for each of these wind farms, it's of the order of 800 to 1200 megawatts. So it's almost like nuclear power plant in the ocean. That's the scale we are looking at. If you move to the next slide, please. And when we talk about offshore wind, we really don't want to look at it just as wind turbines. It's a lot more than wind turbines. It's there are various components of offshore wind that are so critical. And I just want to give a little bit of brief overview. Look at the US market and give a brief overview of what that means. We go to the next slide, please. The offshore wind market in the East Coast, as I said, there are state mandates. There's about 35 gigawatts of state targets. This is just the East Coast, not the West Coast. I'm sorry I didn't include the West Coast, but California just recently they had leased offshore wind areas, and the West Coast also has aggressive targets moving forward. I'll give a little bit of flavor into West Coast. There are technology challenges that we won't go deep into it. We see US East Coast market as a bit more mature when it comes to offshore wind industry, and hence my presentation would be focused a little bit more on the East Coast and less so on the West Coast. Not that it's not important, it's just that we have very little experience. So in the East Coast, there is 35 gigawatts of state mandates, a lot of it coming from New York, New Jersey, Massachusetts, Virginia, Connecticut, North Carolina, Maryland, and Rhode Island. And all these, if you look at the US map, they're all neighboring states. And it's the Eastern Interconnect that would be seeing significant amount of offshore wind farm. Across these states, a total of 17 gigawatts have been procured by the states. That means there are awarded offshore wind contracts. And a lot of these projects are under development. They are being designed and built as we speak now. And most of these offshore wind projects are going to come online by the end of this decade. That's around 2030. Before 2030, you would see a significant amount of offshore wind in the East Coast that is in commercial operation. So the grid would be seeing a new technology at that point, end of 2030. If we go to the next slide, please. This is something I want to spend a little bit of time because offshore wind is very different from onshore and onshore renewable for that matter. So transmission plays a significant role. And a typical offshore wind farm would have generation and transmission. And most of the grid interaction is generally decided by the onshore equipment or the onshore transmission and the transmission network that is in there between offshore and onshore. The wind turbines itself are typically located in the ocean. And generally we have the wind turbines about, I think the closest we've had is about 10 nautical miles away from the coast. And most of them are far away in the ocean and they're spread out. So a typical gigawatt scale offshore wind, for instance, we are seeing about 12 megawatt class wind turbines today, 12.4. And one would expect around 95 to 100 turbines in a gigawatt class wind farm. And each of these wind turbines is spread out. In the US, we have a minimum spacing requirement of 1 nautical mile between the turbines. And more often it is much more than that. So it's really spread out. And most often the transmission, the wind turbine itself has its own transformer, a step-up transformer that transforms it to medium voltage. Typically this medium voltage in the US, most of our offshore wind farm, it happens to be around 66 kV. And then there's an offshore substation that you can see on the picture. And this transforms the medium voltage to high voltage. And from there on, you have the export cable. The export cable voltage can be anywhere. It's generally over 100 kV. Most of our designs use up to 275 kV HVAC cables. And this export cable length, it goes from this all the way from the ocean onto the landfall and then onshore. So it could be like 20, 30 miles. And in some cases, a bit over that. And because we have high voltage AC cable, obviously there is a need for reactive power compensation. So we typically have reactive power compensations devices some located at the offshore end and a lot of it on the onshore end. And there are equipment like other balance of plant equipment like filters, Again, that is located most likely on the onshore side. And there is also a transformer at the onshore substation, which scales it to the point of interconnection voltage. There may be other electrical equipment to provide grid support or grid functionality as it's required. If we move to the next slide, please. So offshore wind, it's an emerging market in the US. And what do we mean by that? At the moment, the requirements for offshore wind industry itself, there's very few. The only one that seems to address a bit of on the requirement side is IEEE 2800 standards. Again, it refers back to the onshore POI requirements, not so much in the ocean. And the technology maturity, as far as the US market, it's still in its infancy. And by technology, I just don't mean the turbine technology, but also there are other aspects like we need vessels to install this turbine in the ocean. And that is something we heavily depend on Europe and rest of the world to get those vessels for installation. And then we have the top side, the jacket, the foundation. A lot of those equipment comes from outside US market. Today, even the turbines are from outside the US market. So a lot of these are being shipped and there is very few in-house work being done within the US. And again, is that the right thing for the US market? It's clearly unknown. So there is still lots of discussions going on there. And from a regulatory framework, again, a lot of the, there seems to be a disconnect between different federal agencies. So Federal Energy Regulatory Commission mostly drives the electrical side of things. BOEM, or Bureau of Ocean Energy Management, is mainly responsible for leasing the offshore wind area and permitting us to build these large offshore installations. So there's a lot of missing pieces and there's a lack of coordination between the two agencies. And also if you look at a transmission perspective on the offshore side in the ocean, there's a lack of market mechanism and lack of definition. And a lot of my presentation will also deal with some aspects of this. Again, from an economics perspective, there's a capital cost, which is probably a little bit better understood, and the cost to operate and maintain. Again, we have experience in the Europe, but the ocean waters could be very different. So this salt content and the seabed conditions, they're all very different compared to Europe. And again, there's a learning curve there. From a mandates and a policy perspective, again, states and federal mandates have always been the ones that are driving this industry, and any disconnect there or any inconsistency out there is going to be a challenge for this offshore wind market. And getting back to, again, supply chain, this is a huge bottleneck for the offshore wind industry today. So we don't have a lot of components that we would like to use to develop these big wind farms. As I said, installation vehicles. So to give you an example, some of the large installation vehicles, there's just a handful of them, 2 or 3 of them globally. And if Asia or Europe, there's an ongoing offshore wind construction, a lot of those get booked in advance, several years in advance. And probably we don't have a chance at that point to mature those kinds of designs that require special installation vehicles. If we go to the next slide, please. So just move on to grid forming converters a little bit, since that's the topic for today, and provide you an offshore wind perspective. So before we get there, I would like to define what we mean by grid forming, and that's only presentation specific. I think at the moment there's still this is not to say the industry standard, but we are following a SIGRE definition. So we'll go over what we mean by grid forming for this presentation. And we'll start looking at some of the offshore wind concepts that are out there. If you move to the next slide, please. So for a lot of our discussions, we'll be using the SIGRE definition. This is Task Force 77 that provides the grid forming inverter related definition. In the broadest sense, it's an converter that can regulate both AC frequency and voltage instantaneously. And SIGRE also requires that this converter has the ability to provide reactive current, which is equal to the steady state rating during faults. The synchronous grid forming converter, it's also required to regulate frequency. And a virtual synchronous machine is basically something that has storage which can deliver some sort of an inertial response and some additional energy when required. And for our particular definition, we will be using the broadest sense. Wherever I am going to refer to synchronous grid forming converter or virtual synchronous machine, I'll be explicit, but otherwise by default, a grid forming converter would just mean it's regulating AC voltage and frequency. That's it. And of course has the ability to provide reactive current. So that would be the broad definition that will be used whenever I mean grid forming converter in this presentation. If you move to the next slide, please. So if we look at how offshore wind transmission evolved in the US, first we started off with radial high voltage AC transmission. What do I mean by that? So there's one wind farm, which is about, as I said, 800 megawatts to 1100 or 1200 megawatts that's connected radially to a point of interconnect. It could be one or many point of interconnection, and it's connected through high voltage AC export cable. So there is no shared transmission in this concept. And this was the initial phases of offshore wind development in the East Coast, because we could find point of interconnection very easily for the first few projects. In some systems like New York and New Jersey, we could find some point of interconnection that could take only AC, and that was close enough to the coastline. But as states started procuring additional offshore wind farm, I think we ran out of luck for those really nice point of interconnection. And we were looking at really long distances. And in some cases, it's over 100 miles. So AC transmission at that point becomes technically challenging. And also from a cost perspective, it's prohibitively high compared to DC. That's when a lot of the offshore wind farms started looking at HVDC. Even then it was radial. So most of the other generation projects that are coming up that include HVDC transmission are again looking at radial transmission. That's one wind farm connecting through 1100 or 1200 megawatt HVDC system and coming onshore. And most of this HVDC system is monopole, symmetrical monopole. And I think most designs, probably there were few that were discussed, which was 400 kV symmetrical monopole, but most designs are 320 kV symmetrical monopole designs that would be used for most offshore wind project. And all these are based on voltage source converter technology. So that in the offshore end where you have no synchronous machine, the HVDC VSC technology provides that ability, the grid farming ability that one would need to operate the wind turbines today. And we'll discuss that once we get to that section. And off late, I think this is mostly since 2022 and this year, a lot of the states, especially New York and New Jersey, have started looking at meshed offshore transmission. And New Jersey will go a little bit briefly on what they were looking at, different concepts. And also from New York, what kind of offshore transmission they've been looking at, and how does grid farming play a role in each one of these. If we go to the next slide, please. So if you look at AC connected offshore wind, the state of the art today, we do use grid farming inverters. And again, by grid farming, I just mean those that can instantaneously control AC voltage and frequency. So we do have in some designs, we've had grid farming Statcoms on the onshore end. Again, a Statcom is a balance of plant equipment for our AC designs, where we are using it just to maintain the reactive power requirements at the POI, or the point of interconnection. And the reason we do it is because our wind turbines, if you look at the single line diagram, the wind turbines are located in the ocean. And typically there would be a transformer, a turbine transformer that transforms it to 66 kV. And then again, on the offshore substation side, you have another high voltage transformer that typically transforms it to 275 kV. And then you have this long export cable. So if you take into account all the impedances and the transformer impedances, the cable impedances, there's really no way we can utilize the turbine reactive power control capability. So we need additional devices on shore, where most often to meet the grid requirements. And also sometimes we need it just to make sure we can ride through some events. And on the offshore end, we try to minimize our equipment as much as possible. Again, we want to restrict the offshore substation size and weight. So we put in some fixed shunt reactors, very minimal one that's required. And on the onshore side, we have typically harmonic filters, then variable shunt reactors, and of course, a lot of balance of plant equipment like Statcom. And some of them, we also use battery energy storage. Again, we use the grid farming inverter technology for that. But most often our turbines are always grid following when it comes to offshore. So in the ocean, a lot of the vendors, at least that we have stated that this is something they're exploring, but for offshore, given the turbine sizes, we are looking at significant challenges with the loads. So the designs still have to consider the turbine mechanical loads or stresses on the turbine. And it's unclear at this point how grid farming would evolve for that. And again, it's mainly because the offshore wind turbine, a typical 12 or 12.4 megawatt turbine, is about 250 meters. And the blade diameter is the rotor diameter is about 230 meters. So it's significantly larger. Just to give you a scale perspective, it's almost 80% the size of Empire State Building in New York City. So it's almost like putting Empire State Building. Each turbine is as big as an Empire State Building, and you're putting them in the ocean. So obviously any control change, they have to do a more in-depth analysis on the turbine loads itself. And hence grid farming inverter is still in its infancy for the offshore wind turbines. Some of our designs, most often we try to use grid for inverters for Statcom. But as I said, there have been exceptions when we have actually used grid forming inverter for the Statcom. The other balance of plant onshore equipment, again, if we see very weak grid at the point of interconnection, we've had synchronous condensers at those to improve the grid short circuit and the grid strength onshore. So that's typically what's done today. If we move to the next slide, please.
Okay, Divya, quick time check, roughly around 15 minutes, that we have some time for questions also.
Yes, absolutely. Yeah. So I should be, I should be done most of. Again, from a grid forming technology perspective, the Statcoms, they are generally located onshore. We've had Statcom with grid forming capabilities, again, just for low short circuit at the POI. That's kind of the application where we have used it. From an offshore perspective, so far there's no commercially available offshore wind turbine with grid forming capability. And again, battery energy storage, we have included in some of our designs because there was a request to have black start capability. And the battery energy storage would provide that. If we move to the next slide, please. We'll look at the radial HVDC transmission as of today a little bit, and then I'll go into the more challenging, more open spaced offshore transmission. So if we move to the next slide, please. The HVDC connected offshore wind, typically we have voltage source converter HVDC system. And rectifier is always in the offshore end. The inverter is on the onshore. And the rectifier is the one that has grid forming capability. And not necessarily any kind of inertial response capability. It just has basic grid forming capability in most designs. And the turbine itself and the HVDC inverter onshore end, though, they're always grid following. So there's a little bit of nuance on the onshore end where we cannot expect it to have grid forming capability for the VSC HVDC. And again, the standard component would be filters that we always use and converter transformer for isolation. So if we move to the next slide, please. So from a grid forming technology perspective, it's only the rectifier, as I said, the VSC HVDC rectifier on the offshore side that has grid forming capability, but most often all the others are grid following. We go to the next slide. So the next set of slides, I would really like to focus and spend some time on meshed offshore transmission. This is immature at this point, and it's evolving. And before we get there, I do want to set the framework up and provide some insights into the kind of challenges we are seeing. So if you move to the next slide, please. So I think one of the things we would like the industry and also the regulatory organizations to recognize is offshore transmission in US is probably different from onshore and requires a different framework. And what do we mean by that? So at the moment, there is no clear reliability framework set up for offshore transmission. And if you look at the offshore wind lease areas, New York and New Jersey, it's literally almost the same lease area or the adjacent lease area that one would be connecting. So the point of interconnection is either going into New York ISO or it's going into PJM. Now, if there is an offshore transmission that connects the offshore lease area that's going and connecting to New York point of interconnect and PJM point of interconnect, again, we don't know what that would look like. So the reliability, who defines it, is unclear. Is it NPCC or is it reliability first? So it's very unclear at this point. From a planning and interconnection and market mechanism, again, offshore transmission, it's unclear who actually specifies this. The states have been very aggressive and moving forward with requests for building out such an infrastructure, but it's very unclear on how ISO would plan these out and what kind of market mechanisms would be set up. From a legal and regulatory framework, again, there is no clear boundary sometimes between generation and transmission. So again, there's a need to have those separated out and define what offshore transmission assets are and how this legal framework would look like. And from a standards perspective, again, offshore transmission equipment standards, it's unclear. It's not very clear, especially when it comes to HVDC, if they would be able to operate together, if multi-vendor HVDC systems could operate reliably. If we move on to the next slide, please. I'll quickly go through some of the offshore wind transmission concept, but before we get there, I just want to start talking a little bit about offshore transmission and the challenges the industry faces. So if you move to the next slide, please. So one can view offshore wind as 100% IBR. So it is 100% inverter-based generation and transmission. And what kind of requirements do we have? It's unknown today. And what is also not known is, do we want bidirectional power flows? That means, do we want the power to be flowing from the onshore end all the way looping back to the offshore and going to another onshore POI? Do we want that? Is there any studies to show that it has a benefit? Maybe there are, but is it something that is valuable enough to offset some of the challenges one would see in offshore industry? So that's really where the open space is, and an opportunity is really defining what this requirements and what kind of technology standards would one need in this kind of a setup. So if you move to the next slide, when you're defining standards or requirements, one of the things we don't want to forget is some of the realities of offshore wind. So permitting and environmental aspects, it's a big part of offshore wind. So you cannot be bringing in requirements that say would require multiple offshore platforms or offshore substations, and then you're suddenly looking at permitting nightmare. So in this map, you can see some of the marine sanctuaries. We just cannot locate some of the substations very close to the coastal waters. And if we go far away from the coastal waters and locate our offshore substation platform, you're looking at really sea depths of several hundred meters. And it is especially a big concern when it comes to West Coast. You could look at ocean depth of 800 to 1,000 meters. And so far, we don't have floating technology that can handle that level of ocean depth. And now you're looking at putting a large substation, a converter, maybe if it is HVDC, a large HVDC converter station on these platforms, where we have no idea how to build that. Even when we build it, there is operation and maintenance. So we have to send crew out. So if it is deep in the ocean, it becomes a challenge. We have been using, for instance, for a lot of our O&M, we have been using drones. And we are trying to do it without people as much as we can. But again, sometimes you just can't help. You have to send people out. And that's a huge problem. So if we move to the next slide, please. Again, one of the things is water depths. As I said, West Coast, we are looking at 600, 800, up to 1,000 meters in water depth. The East Coast is slightly better. Most of our offshore wind farm, the water depth is about 30, 40 meters. So it's, we are bringing in there, it's less than 100 meters. And we have fixed monopile technologies that are fairly mature and can handle this ocean depth. But again, there are challenges when it comes to locating them. A couple of them is the UXO. So it's called as the unexploded ordinances, like there are bombs and all kinds of sunken ship, all kinds of things in the ocean. So you may find electrically, that's the best part to put, let's say, a reactive compensation, but practically you can't because of the UXOs or because of the permitting challenges or because it's a ship lane. So if you move to the next slide, please. Again, just to reiterate, ocean is a shared space. So we have fishing, we have commercial vehicles. We just can't put in our offshore equipment wherever we like and we want. Our designs have to be constrained in terms of locating them. So defense, oil and gas, sailing, and commercial vehicles, all of them share the ocean space. And in fact, when we get the ocean lease, we just get the lease for the generation. We don't actually get the lease for transmission. What our ocean lease says is we'll get right of way to get power out of the federal waters. That's all BOEM says. And BOEM can always tell us you can't go through some protected areas, or you can't go in through shipping lanes, for instance, in which case we'll have to come up with a different design. So that's reality of offshore wind. And if we move to the next slide, I'll just give you a quick overview of the transmission concepts that are being proposed by the states. So next slide, please. So this is one of the things that New York, in its latest New York 3 RFP requested. So they asked us to build offshore wind farm with HVDC connection, like radial offshore wind farm with HVDC, but keeping in mind some possible future expansion. So the RFP actually asked us to put in to include some space on our offshore substation or offshore platform to include some possible future expansion, which would mean connecting 230 kV AC cable, which is 20 to 40 miles long. So that's kind of the specification that was provided. Again, there was lots of engineering details that was missing. This is probably one of the requests that were not fully thought through, and there were lots of challenges. And again, there's no, at least to the best of our knowledge, we don't know if the vendors can guarantee interoperability between two different HVDC lines and converter stations. So there are lots of proprietary control in the VSC based HVDC, especially if it's grid forming. And from an ISO perspective, it was unclear if the ISO had studied reliability concerns, especially when you're joining two different POIs via an AC interlink in the ocean. If you move to the next slide, please. So the benefits, though, is if when you have a grid forming rectifier, HVDC rectifier, the benefit obviously is you don't need a grid forming turbine. And there is a possibility to also enhance the grid forming DC rectifier station to provide other grid services without too much of a challenge. But the bigger challenge we have is the converter station platform becomes really huge, and it's expensive and takes a lot of time to build them. And again, when I talk about time, it includes the foundation, the vessels, and how we have to schedule these large installation vessels to build this heavier station. And what's unknown, again, there's proprietary controls. So it's very hard to analyze and guarantee compatibility across multiple vendors. If we move to the next slide, please. This is something, this was another concept that was thought through in Europe to avoid some of the proprietary issues. So the thought was to have diode rectifier. This is a simple 12 pulse diode rectifier in the ocean. And there's a significant reduction in the weight and the size of the offshore platform in this setup. And interoperability is not an issue. It's a simple diode rectifier and you don't have any fancy controls. So most of it would be driven by the offshore wind farm, which means offshore wind farms need to have their own reference. So you have to have some sort of grid farming capability in there. And you could plan to connect them in different ways. So literally like synchronous machine in the ocean. And again, the thought was you would have studied the reliability a lot better on the onshore end. So if you move to the next slide, I've just summarized some of the benefits. So it's smaller converter platform and no proprietary controls. But the challenge again was the power flow direction cannot be reversed and you need grid farming capability for the turbine. And it's very hard to provide any type of grid service if you want later on in the future. So everything has to be done from the wind farm end, and you absolutely cannot move the power from, so you can't convert the diode rectifier to operate as an inverter. So that's a big no-no. So the power flow has to be in one direction. So I think if we move to the next slide, please. One of the things I would like to this audience to think about is, do we really need grid farming inverter for every offshore equipment? Given that grid farming HVDC could be challenging in the ocean, and maybe the turbines, it's still unclear. So do we really need that? And if you move to the next slide. So some thoughts is, again, probably not. That would be an overkill and overdesign. And we are constraining already constrained supply chain. So the bigger challenge or the bigger piece of the puzzle that needs to be solved before we get to grid farming is probably defining what a regulatory framework would look like and having a multi-state roadmap. So New York, New Jersey, Connecticut, all the coastal states sit together and define what this is going to look like, and what are the points of interconnection for offshore wind. And the optimal options or the best options is not necessarily that's the lowest cost, although cost is a driver, but there are other things like environment permitting issues, and also from a maintenance perspective, installation and transportation perspective, all these need to be looked at holistically. And of course, the technology standards, there are already upcoming initiatives in Europe. So one may want to align some of those when it comes to HVDC technology standards and those development of those standards. So if you move to the next slide, please. I think one request, again, I would have is for the industry to be a little open when it comes to standardization. Standards are absolutely essential to enable interoperability across vendors, but we also want standards to provide flexibility to allow innovation. And I think one ask would be standards, the technology roadmap, policy and regulatory framework, all of them are well aligned. That would be a perfect world. And one of the challenges is in the ocean, anything you want to retrofit is going to be expensive. And sometimes practically not possible. If you want to put another offshore platform, like the one that's shown in figure, which is an AC offshore platforms. So if you want to put another AC substation in the ocean, it's a significant hassle. It's not easy to locate wherever you think is electrically the best part. So you may decide electrically that's the best part, but maybe there's a fishing lane and you just can't place it there. Or maybe the size of this platform is so large that there is no installation vessel in the world that's been developed to install this. Or maybe it's a maintenance challenge, especially when it comes to floating. We should have some equipment to be able to do maintenance on those large floating topside. So if we move to the next slide, I think it's a great opportunity to define the future grid for offshore. One could imagine 100% IBR scenario. But again, with that, with an opportunity, there's also a cost. You want to do it in the right way. So if you set up a wrong standards, wrong requirements, it's going to be a challenge down the road. If we move to the next slide, I'll conclude, and I think I'll be on time. So again, this offshore industry at the moment is in its infancy, so it's an opportunity to plan for the future offshore grid. But I think there's a need for a holistic approach, looking at technology, cost, regulatory framework, O&M in the ocean, and the realities of the ocean. Ocean is a shared space. And given that a lot of us here are researchers and we want to come up with innovative ideas, this could be a perfect framework where you're looking at 100% inverter-based technology, and you could come up with more innovative requirements. You don't have to probably look at synchronous machine requirements. It could be something ground up, more fundamentally different. And whenever you come up with anything, they have to be evaluated for different offshore systems, and make sure that indeed the O&M, the cost, the infrastructure to build this is out there, or at least out in the time frame you're looking at building these. With that, I think I would like to thank you. If you go to the next slide, please. Thank you so much for your time and for your interest, and I'll be happy to take up.
Thank you so much, Divya. We do have some time for a few questions.